Alright, so we're going to talk about the nomenclature or naming of covalent compounds. And in terms of naming, there are lots of ways to classify things. You can classify the same set of stuff in different ways. We could classify you according to boys and girls. We could classify you according to height. We could classify you according to length of hair or race. What? All kinds of ways we could classify you, okay? So just because I'm choosing to classify covalent compounds according to the nomenclature, naming systems, doesn't mean you can't classify it in other ways, okay? But we're going to classify them in terms of naming. Okay, two classes of nomenclature. The first one is non-organic and organic. Okay. Now, covalent compounds are all held together by covalent bonding. Which means the sharing of electrons. The method that we use to show how that sharing takes place in here, we covered in the last unit. Okay, we spent a lot of time with electron dot formulas and then showing using those electron dot formulas how you share electrons. We call that the sharing arrangement. Then we, from the sharing arrangement, wrote Lewis dot formulas. Okay? For the most part, Lewis dot formulas are used to show how you share electrons. And so it's most of the time used for covalent bonding. It's a way to figure out the structure of molecules, or at least a starting place to do that. And we use it that way. We use Lewis dot formulas to figure out how the electrons are shared, and then we went about trying to figure out what the bonds look like, or what the shape of the molecule was. Remember that? Okay, and we're going to revisit that in this unit. So you have to know how to figure out the shape of a molecule before you can figure out the polarity of the molecule, and that's also part of this unit. So if you don't remember how to figure out the shape of a molecule, you need to go back and review your notes. It's very important. Or go back and look at the video on YouTube. Okay? All right, now, what we're going to start with then is this class called non-organic. It's sometimes easier to define what non-organic is when we first define what organic is. In a sense, I'm going to define non-organic by defining organic. Okay? So non-organic are typically made of non-metals bonded to non-metals. And that's what all organic compounds are. I mean, all covalent compounds are. They're non-metals, typically bonded to non-metals. Okay? But the non-organic ones don't have carbons bonded to carbons. Okay? So non-organic compounds are typically made of non-metals bonded to non-metals, as are all covalent compounds. But the difference for non-organic is you don't have carbon atoms bonded to other carbon atoms. And that's essentially the definition for organic. Organic is carbon atoms bonded to carbon atoms. Okay? Non-metals bonded to non-metals, but in particular, somewhere in that structure, in a covalent, in an organic compound, you're going to have carbon atoms bonded to other carbon atoms. Okay? All right, now, these are the compounds that we use prefixes for. Okay? I'll give you an example of non-organic first. This is a non-organic compound. Okay? So we have a carbon atom in the formula, but there's no carbon atom bonded to another carbon atom. This is one carbon atom bonded to 4 chlorines. Okay? So we got one carbon. I'm using Lewis dot formulas, or a Lewis dot formula here. This is one carbon atom bonded to 4 chlorine atoms. Did I say carbon? I say carbon bonded to chlorine, right? I hope. Okay. All right. So that is an example then of a non-organic compound. There is a carbon there, but for it to be organic, it has to be one carbon bonded to another carbon or more than that. Somewhere in that structure. Okay? So okay. So non-organic covalent compounds are named using prefixes. That tell the reader or listener how many of each element or atom really is in the formula. So if I have a formula, I can determine the name using these prefixes. If I have a name, I can determine the formula by using those prefixes. Does that make sense? Okay. The example is of this up here. CCl4 is, there's only one carbon. We just call that carbon. There are 4 chlorines, and the prefix for 4, or one prefix for 4, is tetra. So that's carbon tetrachloride. Okay? Now the chlorine in this particular case is not an ion. We don't call it chloride because it's a negatively charged ion. That's what we learned about, or have learned about ide endings so far. They're reserved for monoatomic anions, negatively charged single atom particles. Okay? But when we get to covalent bonding, there's no real charge here, but you always, nevertheless, name the last element in the formula with an ID ending. Okay? Clear with me on that? Any questions? Okay. Now, as far as which element gets written first, both in the name and in the formula, generally speaking, but not always. This is a review from Unit 3. Generally speaking, but not always. You always list the least electronegative element first and do them first, least to greatest. So in this formula, chlorine has a greater electronegativity than carbon. So carbon having the least electronegativity is written first. Does that make sense? Both in the name and in the formula. Now, if you don't remember, on the periodic table, the most electronegative element is fluorine. We generally consider these noble gases over here to have no electronegativity. And so generally speaking, the pattern is that it's highest up here and lowest down here. Okay, remember that? And in this unit, we're actually going to look at a periodic table that has the electronegativities written out for you. This is in your set of test references. Okay? You might want to get those out if you don't already have those out, and make sure you know where those are. Okay? Because when we're figuring out the polarity of molecules, you need that. We don't need it right now, but we'll need it. Okay? So here's the periodic table of electronegativities. All right? And if you're struggling with the idea that it's highest up here and lowest down here, and just knowing by where it sits on the periodic table how to write which element before the other one, you can always go here and look and write the one that's smallest first. Yes?
On the note gases, why does 18 have sometimes
What now? What?
18 has
Okay. I said, generally speaking, we consider the noble gases to have no electronegativity, correct? Okay. So generally speaking means there are exceptions. And in fact, you can get xenon, even though it's a noble gas, you can get xenon to bond with other elements. And that's why it's assigned an electronegativity. Okay? That's a good question, though. Very observant. Okay? Now, let's look at what the prefixes are. The prefix for 1 is mono, but we almost never use it. The prefix for 1 is mono. We almost never use it. In this class, I can't think of a compound where we'd actually use mono. We might, because commonly it's sometimes used, but about the only time we use it with any regularity. Let's just say only, because you understand that there are sometimes exceptions. This is only used for carbon monoxide. Okay? And carbon monoxide is capital C, capital O. Okay? We've learned about carbon dioxide in the last unit. We use that for figuring out the shape of bonds and molecules and such. Carbon monoxide has only one oxygen in the formula, where carbon dioxide has 2. Carbon dioxide is not considered poisonous. Carbon monoxide is. Both can kill you, but it's just like water can kill you, but it's not considered poisonous, okay? Does that make sense? I mean, you're breathing in both carbon dioxide and carbon monoxide all the time. It's just the amount. It's always the amount that'll kill you, okay? Like we talked about in Unit 2 with radiation. There's all kinds of radiation in this room right now, but it's the amount that matters. A small amount of gamma radiation is not going to hurt you, but the larger, more and more amount, the larger and larger the amount of gamma radiation you're exposed to, the more likely you are to have permanent damage and could cause your death. Okay, so that's 1. We almost never use it. 2 is di. 3 is like tricycle. Yeah. 4, tetra. We already learned about that one. 5, penta. Like the pentagon has 5 sides. 6, hexa. And I like introducing hexa here right before Halloween because what you know what witches do?
Nope.
You don't know what witches do?
Oh, I wouldn't do it.
They cast
Okay.
hexes on you.
What?
Huh? You don't know what a hex is? It's like a spell. You know that? Now you know. New word. There you go. All right, a hex. All right? And if you got 3 hexes, that's really, really bad, right?
That ain't good.
We're in the Bible Belt, so if you're not in the Bible Belt, you might not know what we're talking about. All right. You get it now? Oh, I heard that. Oh! Okay. 8. Octa, like an octopus, has 8 arms, 8 tentacles. 9 is nona. 10 is deca. Like 10 years is a decade.
Will we actually go this far? Naming elements?
Naming compounds.
Yeah.
Yeah. Well, maybe not. Well, there are some, but you need to know all 10. Okay, you need to know all 10. All right? Any questions about all that? Then let's practice. Okay, well, this isn't a request. It's kind of like Mission Impossible. You know, it's your job whether you choose to. No, that's Mission Impossible. You choose to accept it, right? You could turn it down. It's not like Mission Impossible.
You were forced to accept it.
Yeah, you're forced to accept it.